我介绍一下，就是我们的这一期读书会主讲人是 Karl Friston，他这一次主讲的题目是意识的物理学、主动推理的顶层逻辑，就是主动推理两层路径里面的 High Road。然后我简单介绍一下 Karl Friston，他是理论神经科学家、脑成像领域的权威，目前在英国伦敦大学学院是任教授，是英国皇家学会院士、欧洲科学院院士。我可能得那个有朋友有声音的话可以关一下。然后他是统计参数映射 SPM，这个是他引文最多的一个工作。还有就是体速及形态测量 VBM，动态因果建模 DCM，就是这三个非常重要的技术的发明者。然后这些研究受到了对精神分裂症和价值学习的理论的启发，他提出了精神分裂症失连接假说。此外，他还在数学方面做出了重要贡献，包括变分拉普拉斯程序和用于层次贝叶斯模型繁衍的广义滤波方法。他还致力于研究人类大脑中功能总和的模型以及神经元相互作用的基本原理。他在理论神经生物学方面的主要贡献是自由能原理和主动推理。一会儿就是我们的主持人张俊老师会对他就是这些工作有一个很有意思的解读，大家一会儿可以期待一下。然后我介绍一下我们的圆桌嘉宾。然后首先是张俊老师，他是上海数学与交叉科学研究院和密歇根大学安大堡分校的教授，他也是就是这个研究院的创始人之一，他会作为我们今天的主持人来主持这次活动。然后第二位嘉宾是汤雷汉老师，他是西湖大学理学院与交叉科学中心讲席教授。第三位是张江老师，他是北京师范大学系统科学学院的教授，也是极致俱乐部极致科学研究中心的创始人。第四位是牟慕云博士，他是北京师范大学系统科学学院的博士生。第五位是张正全博士，他是复旦大学信息科学与工程学院的博士生。然后其实还有一些老师也是就是对这个话题非常有兴趣，然后可能因为时间啊各方面原因没有列上来。然后就是老师们如果有问题的话，就是可以不管是加入问答环节，还有圆桌环节都非常欢迎。还有各位老师朋友都可以加入讨论。然后今天的报告的内容就是主题就是意识的物理学、主动推理的顶层逻辑。然后我们最近也做了很多的推文宣传，可能很多朋友也关注到。然后它的那个出发的问题就是我们如何理解作为有意识的生物。然后自由能原理和主动推理，它或许可以提供一个解释。今天分享的大纲首先是主动推理的两条路径，一个是 high road 物理学角度，一个是 low road 神经生物学角度。然后是贝叶斯力学与自证性，第三部分是大脑中的贝叶斯信念更新与预测加工。这部分就是跟 Friston 沟通的时候，其实就是像我前面说的，我们读书会在发展的过程中，可能大家主要还是聚焦在那个 low road 的神经生物学的角度，对于物理学这个角度还没有做很多的梳理，所以就是我们这一次就是也邀请 Friston 是会更注重物理学这个角度，希望能够对大家有更多的帮助。然后这个部分我们也希望在后面的读书会中有更多的讲解，尤其是非常欢迎物理学方面的那个朋友，如果有兴趣的话，可以参与我们的读书会，来就是一块儿去探索这个领域。
Thanks, Dr. Friesen, for accepting the invitation to give a presentation to this club, and we very much look forward to that. So I think people here have gone through several iterations of the free energy theory of brain function based on your papers. So I think it would be very nice and here that we gather here to actually listen to the inventor of the theory to give us an overall view and as well as the future perspective of this theory. So my name is Jun Zhang, and I'm a professor at the newly established Shanghai Institute for Mathematics and Interdisciplinary Science, and also a professor at the University of Michigan, Ann Arbor. I had the privilege, I think, of visiting Professor Friston back in July of 2017 I don't know whether you still remember that, but I actually gave a talk on information geometry. I have been very interested in this theory, that is trying to unify the brain functions. So I think that theory really works well with the theory which I was working on then at that point, which is information geometry. So as someone who had worked in neuroscience for many, many years, the first time I heard about Professor Friston's work is really on a different topic, the tools that he invented for functional neuroimaging. So Professor Friston is a world-known neuroscientist. In preparing for this introduction, I actually did a Google search, and not surprisingly, his citation, according to Google Scholar, is #1 in the tag of neuroscience, with an astounding 347,000 citation, and with an H index of 273. So by way of comparison, I looked at, say, people like, who are very hot in machine learning, like Yann LeCun, who get a citation of #6 in computer vision, for instance, and also Jeffrey Hinton, who is #1 in machine learning and AI. As you can see, Professor Friston's I10 index surpasses both of them, as well as the H index surpasses both of them. And the reason is that if you count the number of publications, I was just so astounded to find that Professor Friston has written like over 2,000 papers according to Google Scholar citation. So that's just a completely amazing, to me when I studied this by way of introducing Professor Friston's work. And the next slide, the next one, let's go to the next slide. And so I looked through the citation history. So of course, Professor Friston was known to the neuroscience community for inventing the so-called, statistical. Yes, can you hear? For inventing the statistical parametric maps that was used in functional neuroimaging. So based on that work, he's so well known by the neuroscience community. But in 2000s, in I think the middle of 2000, the first decade of the 2000s, he again invented this free energy principle as a unified theory of brain function. And I was trying to locate the first paper that Professor Friston may have mentioned the word, or the first influential paper that may have mentioned the word of free energy model. And the one that I found is a 2005 paper, A Theory of Cortical Response, in which he articulated the theory cortical response can be seen as a brain's attempt to minimize the free energy induced by the stimulus and thereby encode the most likely one. So that theory essentially unifies the existing viewpoints or hunch about the basic operations of the brain using, like, as old as, say, like the Helmholtz principle of perception, as perception as unconscious inference, and the idea of predictive coding and Bayesian brain hypothesis, and so on and so forth. But I think the uniqueness of his work is he introduced this idea of free energy, which is a very familiar concept to physicists, into neuroscience, and is able to actually unify the previous existing kind of approaches by this theory. So we're very fortunate to have him come to us and to explain his motivations for this theory. And I would like to point out by looking at the citation. So here on the left, the citation counts for the, well, okay, you have the next slide, right? Oh, no, the previous slide. I think the previous slide gives you the total counts. Yes, the previous slides give you the total counts. But if the slide I was just referring to tells you the trend of his work, of the publicity of his work. So the next slide. So you can see the SPM work is being widely popular in neuroscience community. In fact, anyone who is doing neuroimaging cannot do anything without using the SPM tool. Now, the free energy principle, as you can see, is on the rising phase. So let's just try to catch that wave of his unifying brain theory, and let's hope to eventually find a solid foundation for understanding how the brain functions. So with that, I would like to pass it on to Professor Friston. Let's give him a warm welcome.
Well, thank you very much for that lovely introduction. I think that's the nicest introduction and certainly the most thorough introduction I've ever had. So thank you very much. If it's been recorded, I'll try to put that in my CV. That's,
Okay.
And 2 points. If you want to have a very high I10 or H index, the secret is just to get old. So you just have to wait. And when you're older, you write a lot more papers. And also, information geometry is at the heart of what I'm going to be talking about. In fact, I could give this presentation just looked at through the lens of information geometry. But we'll see whether that comes across in the presentation. So let me repeat my thanks, not only for that wonderful introduction, but also for the opportunity to speak to you today. I've been asked to talk about the high road to active inference. So what I'm going to do today is describe the physics backstory, or the principles that come from physics that can then be applied to brain function in the form of active inference. So much of this is going to be conceptual. I will rely upon a certain kind of mathematics, but I will try to make it intuitive so that you can see where some of the objective functions that we use in active inference come from, how they emerge from very simple considerations of what it is to be a self and to have self-organization. So the talk is going to have effectively 3 parts. I'm going to start by telling a story from the point of view of physics, with a special emphasis on Markov blankets and what arises from Markov blankets, namely a Bayesian mechanics that allows you to interpret self-organization of anything, a particle or a person, in terms of them making sense of the world in which they find themselves. I'm then going to tell exactly the same story, but now from the point of view of predictive coding. We've already mentioned Helmholtz and notions of unconscious inference, and I'm going to tell the same story as a physicist, but using the language of a neurobiologist or a neuroscientist, or indeed a psychologist. And then if we have time, I want to conclude with the denouement, or the extension of these arguments from simple self-organization of most things that we see around us, through to the kind of self-organization that you and I enjoy, basically the self-organization that underwrites agency. And to put it very, very simply, why things like us have the ability to plan and think about the future. But let's start with a question posed by Schrödinger. How can the events in space and time, which take place within the spatial boundary of a living organism, be accounted for by physics and chemistry? What I want to do here is not answer that question, but focus on the notion of a spatial boundary and how important that is when you want to talk about self-organization or anything pertaining to an agent. To be able to define the self, one has to be able to distinguish the states of oneself from everything else. And that individuation, that separation between the states of some thing, some entity, and the rest of the universe, I'm going to associate with the notion of a Markov blanket. So for people who do not know what a Markov blanket is, I've tried to illustrate it here. So if we consider a very small universe, where the states of the universe are denoted by these nodes here, and identify the states, say my states or my internal states, with this blue disk here, then the Markov blanket are the set of states that effectively separate me from the rest of the world. Statistically speaking, what that means is that if I wanted to know how my states will evolve in time, I only need to know my blanket states. I don't need to know the rest of the universe. All the information about the rest of the universe exists on this boundary or set of blanket states. So in that sense, these boundary states or blanket states insulate me from the rest of the world and allow me to be identified as my internal states and my blanket states. The edges or the arrows here denote an influence of one state on another state, and technically the Markov blanket is constituted by the parents, the children, and the parents of the children of the internal states. And I've made a second move here. I've divided the blanket states into sensory states, which influence but are not influenced by internal states, and active states that influence but are not influenced by external states. And with that partition or that separation into different kinds of states, I can now talk about the states of a particle or a person in terms of particular states, where those particular states constitute the internal states and the blanket states themselves divide into sensory and active states. You may be asking why I've divided things into sensory and active states. I'll illustrate that with a couple of systems of particular interest. For us, the brain is clearly one of the key systems, but we can also apply this partition to anything really, and I've illustrated that with a cell here. So what are the internal states of the brain? Then they would include all the neuronal and synaptic activity, all the connections that I would need to list in order to describe the state of my brain. And the state of my brain then causes changes in active states, my actuators, my muscles, my autonomic reflexes, that change my external states, could be the states of my body or states in extrapersonal space. And then these external states then change the sensory states, which in turn change the internal states, where the sensory states could be my interoception, it could be my visual inputs. So what we have is a separation between internal states, the inside and the outside, where the outside influences the inside through the sensory states, and the inside influences the outside through the active states. So very simply, you can think of the Markov blanket as the inputs and the outputs that separate a particular system, here a brain, from everything else that can influence or be influenced by that internal state. Exactly the same arguments can be applied to a single cell, where the active states could be the actin filaments that push the sensory states into the external milieu, which activate cell surface receptors that then change the intracellular states, and so on. It's exactly the same circular causality that can be conceived of as an elementary kind of action perception cycle. What I want you to do now, though, is to forget about the Markov blanket. What we are going to do for the next few slides is just think about the physics of self-organizing systems. And then we're going to put the Markov blanket back into the framework and see what emerges. So this is going to be a very brief rehearsal of physics, starting with a random dynamical system where we have the rate of change of these states x as a function of where we are in state space, plus some random fluctuations. And I've cartooned that here in terms of just two states. And these states can be evolving over time at any temporal or time scale. It could be a very fast time scale. It could be the fluctuations and the voltage and conductance of a single cell in my brain. It could be my cardiac cycle as I work through my cardiac cycle. It could be me getting up in the morning, having a cup of coffee, doing my emails, having my dinner. It could be changes over the year, from the beginning of the year to the end of the year. The key thing about this kind of object, this description of, say, me, or different parts of me at different scales, is that I always keep returning to the same kind of states after a suitable period of time. In other words, I possess characteristic states that characterize me, and I'm generally found in those states and not in all of the other states I could possibly occupy. If I was in these other states, I wouldn't be me anymore. They would not be characteristic of me. So we can think of this object as an attracting set, a set of characteristic states that I move through, keep revisiting from time to time. Or we can conceive of this as the probability that you will find me in any particular state if you sample me at a random point in time. And that's what I'm illustrating here. I'm interpreting this object as a probability density over the states, given I am me, given the characteristic states that characterize me. And the reason I've done that is that we can now appeal to a vast body of work in physics that describes the evolution of these characteristic states, or this attracting set, technically a pullback attractor. I've written one example here in terms of the Fokker-Planck equation. I could have written a time-independent Schrödinger equation or some master equation. They're all effectively saying the same thing. It's really important what they're saying. What they are saying is the rate of change of this probability distribution can be expressed in terms of the flow that constitutes the dynamics of the states and the amplitude, gamma, of the random fluctuations. And that's important in the following sense. I've just said that the kind of things that we want to understand are those things that keep revisiting characteristic states. So this probability density doesn't change. So the rate of change, the density dynamics, the P dot, is 0, which means I can rearrange this equation here in terms of a solution. This is a simple example appealing to something called the Helmholtz decomposition. And all it means is that if I am occupying my attracting set, then my dynamics, my flow, must be expressed in terms of the gradients of the log probability density over my characteristic states. I and many of my colleagues, I don't know if Ping is in the audience, worry a lot about how you decompose this. And generally, this is decomposed into a gradient flow, a dissipative part, and a solenoidal flow that circulates on the isocontours of the probability density. More intuitively, we're all used to this kind of dynamics. For example, water flowing down the hole in a bathtub. The circular flow, the solenoidal part, denoted by Q here, would be the swirling around the bathtub hole here, and the gradient, the dissipative part, would be flowing down under the force of gravity. And together, this describes the dynamics, which I repeat, can be understood as flows that have to gather themselves up, concentration gradients or probability gradients, in order to counter the dispersive effects of the random fluctuations. So that's the basic physics of self-organization to non-equilibrium steady states I want to consider. What we'll do now is ask, well, what would happen if we now had a system that had a Markov blanket? In other words, a system that contained some particle or some person immersed in a larger universe. Well, that solution to the density dynamics holds by construction for the internal, well, for all of the states, but specifically let us focus on the internal states and the active states. And the reason for focusing on the internal and active states is that by construction, by the conditional independence of the Markov blanket, these dynamics do not depend upon the external states. So my internal states and my active states must be performing a gradient flow on my blanket states here, the sensory states given me. And I'm going to read this elemental, foundational kind of dynamics in terms of perception, adjusting my internal states and action, adjusting or describing the dynamics of my active states. Under that interpretation, how can we interpret this quantity here? It looks as if both action and perception are trying to maximize the log probability of sensory states given me. So what would that mean? Well, we've just said that this probability scores the probability you'll find me in any given state, and that state is an attracting part of an attracting set. So these are attractive states for me. They have value for me because they are the kind of states I expect to find myself in. So in that sense, we can interpret this log probability as value. And if we do that, then this is just describing things like reinforcement learning. If you're an engineer, it'd be optimal control theory. If you are an economist, it would be expected utility theory. That is nice because the negative of this quantity is known in information theory as self-information, sometimes called surprisal, or more simply, it's just surprise. It just scores the implausibility of finding me in this sensory state, given I am me. And from this, we can say that action and perception are in the service of minimizing surprise, maximizing mutual information in the spirit of the maximum mutual information principle, or the Infermax principle, equivalently minimizing redundancy, and indeed the free energy principle. We'll see later that the free energy provides a bound or an approximation to the surprise. That is interesting because the average of the self-information is known as entropy, which means it looks as if perception and action are trying to minimize, on average, entropy. And of course, that is the holy grail, that is the objective of many ways of framing self-organization, in particular, say, synergetics of the kind introduced by Hermann Haken. And if I was a physiologist, it would just be a statement of homeostasis, just keeping my essential variables, my physiological states, within viable bounds, within that attracting set. There's a final interpretation that I want to pursue that leads to this Bayesian mechanics, and that's the interpretation that a statistician would bring to the table, namely the probability of some sensory data given me as a model of how those data were caused. And that's known as model evidence, which means that action and perception can be regarded as trying to maximize the model evidence for my model of the world. This is also known as a marginal likelihood, having marginalized all the causes, the external states of my sensory data. And this perspective can be read in terms of the Bayesian brain hypothesis, evidence accumulation, and as we'll see later, predictive coding. More generally, you can think of this as self-evidencing, acting and perceiving in a way to maximize the evidence for my model of the world, my world model, or my generative model, or indeed gather evidence for my own existence. Just to quickly illustrate what emerges when you simulate systems under the constraint that they have to possess a Markov blanket to be identifiable as containing something. What I've done here, what we have done here, is to simulate the dynamics of a large number of small macromolecules equipped with strong repulsion effects on each other and weak electrochemical attraction. And then we simply integrate the equations of motion and observe all these little macromolecules bubbling around in a potential well. And you may be asking, why have we done that? Well, the idea is because I've written down the equations of motion, I now know all the arrows in that graph that we saw at the beginning, which means I can identify a set of internal states and thereby identify their Markov blanket and ask the question, is there a little creature, a little thing living in this simulation of, say, a primordial soup? And indeed there is. So this is exactly the same simulation, but now I've color-coded the molecules in terms of whether they are the internal molecules or states, the active states that lie beneath the surface, or the sensory states that protrude into the external states in cyan here. And what we see is that at a non-equilibrium steady state, there is a little virus-like particle with a little tail or cilium here that is self-organizing in a way that we can describe in terms of the free energy principle or the Bayesian brain or self-evidencing. So just to illustrate what that means, what I've done now is ask, well, if this notion of self-evidencing or this Bayesian mechanics is an appropriate interpretation of this kind of self-organization to a non-equilibrium steady state, then I should be able to find numerical evidence that the internal states are in some sense encoding or modeling or inferring or predicting the external states or events out beyond the Markov blanket. And it is very easy to identify numerically this kind of representation or coupling to the outside world through the Markov blanket. So what we have done here is ask, is there any linear mixture of internal electrochemical states, say, as a metaphor for neuronal responses, that can predict or is correlated with motion, modes of motion in the external states? For example, when certain molecules pushed away from the soup and then are pulled back again by the attractive forces. And it is easy to find that relationship mediated by something called a synchronization manifold, where that obtains by plotting the external fluctuations against the internal representation. I'm showing that here in terms of the motion on the outside in cyan, and the prediction based purely upon the internal states with the 90% Bayesian credible intervals. And importantly, the true outside motion always falls within the inferred motion based purely upon the internal states. And this is remarkable because the internal states cannot see, they're not influenced by the external states. They only see their sensory states, the sensory sector of the Markov blanket. I can go further and align all the peaks of this prediction to create a simulated event-related potential that looks very, very similar to the kind of event-related potentials you would get in electrophysiology. Here, an example from a small monkey or animal study. So what are we looking at here? Well, in one sense, we're looking at something which we're all very familiar with, first noted by Christian Huygens in terms of synchronization, either generalized synchronization or synchronization of chaos. So what he noticed was that if you take several clocks and hang them from the same wall or beam, then ultimately they will converge such that they are all oscillating in synchrony. And this is in fact a little sketch from or drawing from Christian Huygens with the beam here and two clocks. So from our point of view, we can regard one clock as containing the internal states, and the other clock being the outside, the universe, the external states, and the beam now constitutes the blanket states. It's how this system or clock is coupled vicariously through the blanket states to this clock. So all we're saying is that this free energy minimizing solution, this surprise minimizing solution, this kind of self-evidencing process is an interpretation of the generalized synchronization between a thing and the environment or the world in which it is immersed. What I'm going to do now is briefly rehearse exactly the same story, but from the point of view of neurobiology. but using the same first principles of self-organization to try and understand how we make sense of our world and indeed act upon that world in order to make the best kind of sense of it. This story goes all the way back to Plato, through Kant, and as we've already heard, is probably best articulated by Helmholtz. But I've taken an example from the 16th century here, using an oil painting by an artist famed for painting still lives, bowls of fruit in this instance, that when viewed from a different perspective, give you a very different impression. So if previously you saw a bowl of fruit and now you see a face, the point he is making here is that you made that face. Your brain is a constructive organ. It's a statistical machine that's generating explanations and predictions of what is on the outside beyond your sensory Markov sector of your Markov blanket, beyond your sensory veil, to provide the best explanation or account that could explain what you are sensing at the moment. Helmholtz, of course, in his notion of unconscious inference, captured this idea beautifully. For example, objects are always imagined as being present in the field of vision, as would have to be there in order to produce the same impression on the nervous mechanism. This idea is clearly very closely related to psychological ideas, for example, those of Richard Gregory, who conceive of perception as hypothesis testing. Again, you have to have the explanation or the percept in your head in order to confirm or disconfirm whether this is a right explanation, the right hypothesis, the right representation, by comparing what you would predict against what you're actually seeing. And if you predict correctly, there should be no error in your prediction and you found the right explanation. Otherwise, you have to engage in this Bayesian mechanics, belief updating or self-evidencing. This notion of sense making has been used to great effect. For example, people like Geoffrey Hinton, who we've already heard about, and Peter Dayan actually built a Helmholtz machine in machine learning as a metaphor for the Bayesian brain, borrowing from Bayesian probability theory, and particularly the work of Richard Feynman on variational free energy in solving difficult inference problems, integration problems in quantum electrodynamics. And that's where the free energy principle inherits. So let's come back to Helmholtz's notion of the impressions on the nervous mechanism. From the point of view of the physics of sentience, what that can be thought of is as shadows or impressions on my sensory part of my Markov blanket, my sensory veil, the veil that intervenes between me, my internal states, and the external states. And I've drawn this in terms of a shadow here. And if this notion of self-evidencing is correct, what it means is I, just by existing, can be described as trying to represent or explain what caused these sensory impressions here. Is it a leap or is there a better explanation? So how might the brain do that? Well, we already know how it does it because we know it must conform to these first principles of self-organization. So we can, what I've done here is just rewrite down that gradient flow with its solenoidal part here, but specifically for the internal state. So the rate of change of the internal states must be a gradient flow on that surprisal, which I've now replaced with the free energy. And we'll unpack the free energy in a few slides. And I'm going to make a move here that the internal states can be interpreted as the parameters of beliefs, variational probability distributions about the external states. And if I do that, then I can rearrange and interpret this fundamental gradient flow in terms of something that you would recognize if you were an engineer as a Kalman filter. If you were a computational neuroscientist, you would recognize this as predictive coding, a description of neuronal dynamics, the rate of change, the flow of internal, you say, neuronal states that can be expressed in terms of the solenoidal part, or divergence-free or conservative part, as a prediction. So if I know the states of the world out there, then I know I can predict what I'm going to see at the next moment in time. And this is a derivative operator here. And then the dissipative part, the gradient flow itself, can be now written as a prediction error. So a prediction error is another way of formulating a gradient on the free energy or the self-information or the surprise. And this, in terms of a Kalman filter, will be known as an update. So I have my prediction based upon what I think is happening out there, and then I use a free energy functional of my sensations to form a prediction error to update my prediction to give me an optimal description about, or expectation about, the causes of my sensations. So let me give you a practical example. Imagine we had this sensory impression on our visual epithelia, on our retina, and that I had this expectation, this parameterization of a belief, that this sensory impression was caused by a howling dog. And if I had a generative model that could generate what I would see if it was a howling dog, then I can compare the prediction with my actual sensory input to form a prediction error. So the prediction error is just the difference between the sensory input and the prediction under some generative model. And all that this equation is saying is that I'm going to use my prediction error to update my expectations, the state of my brain that is encoding my beliefs about the causes of my sensations. And I will do so until the gradients have been destroyed or the prediction error has been minimized, and I will have found the best explanation. But notice the best explanation is not necessarily the true explanation. In this particular example, the cause was actually a cat, not a dog. But I will never know that, because I only need to minimize my surprise or my free energy. And if I can do that for the time that I exist, then that is good enough. So this provides a very simple picture of action and perception in which we can forget about all the physics and reduce everything to a minimization of prediction error. For the physicists in the audience, remember the prediction error is just the gradients of the variation free energy. So how can I minimize prediction error? Well, there are two ways in which I can minimize prediction error. I can literally change my mind, change my brain, my neuronal activity to make my predictions more like the sensations, and we can regard that as perception. However, I can also change my sensations to make them more like my predictions. So how can I change my sensations? By acting upon the world to gather different sensory consequences. Acting, for example, by moving my eyes, by palpating the visual world, actively by looking over there as opposed to looking over there. I could extend this notion of action to nearly every system, autonomic, somatosensory, or indeed choosing which social media channel to solicit information from. So we have a very simple picture now of self-organization in the service of minimizing prediction error, either through perception by changing the predictions, or through action by changing the sensory samples from our world. Here's a more neurobiologically grounded example of this kind of self-evidencing, this Bayesian mechanics, this predictive coding. I've sketched out here a rough functional anatomy of the visual system where we've got some visual sensations arriving at the lateral genicular body, that are in receipt of top-down predictions from expectations, the mu of the previous slides, so that we can form a prediction error that is then sent back up to revise or update our expectations according to our fundamental flow equation here. But of course, these expectations are themselves in a hierarchical generative model being predicted by higher order expectations. And these are used to form a second order prediction error that then is used to update the expectations at the second level, and so on to any depth that you would like to consider. But let's think about a different kind of input. Let's think about proprioceptive input from the eye muscles. This comes in, say, to the nuclei in the brainstem, the pontine nuclei, and I could predict what I am sensing from my eye muscles. I could predict where I am looking at the moment, and that would create a prediction error, and I could use that prediction error to revise, update my beliefs about where I am currently pointing my eyes. However, there's a much simpler way that I can reduce this prediction error, and that's by acting. And I can act upon the world simply by sending this prediction error to the muscles to cause them to contract until the report, the proprioceptive report of their tension matches my predictions. So this is a very simple example of changing the world, actively changing the state of the world in order to make my predictions come true. And all that I have described is a simple reflex arc. This is how we actually move, either with our motor system or indeed with our autonomic reflexes. On this view, the predictions now play the role of a set point, a target that is now realized through action reflexively in a very, very simple way, in a closed loop way. But notice that these predictions themselves come from a very open loop, deeply informed hierarchical synthesis of all kinds of different sensory inputs or modalities. So we have a deeply informed control supplying predictions that are then realized reflexively by our motor system or our autonomic system. I'm now going to just finally take us one step further. But before doing that, let's just rehearse how far we've got in terms of understanding the computational anatomy that emerges from this consideration, either from the physics of self-organization or from the Helmholtzian notion of sense-making and prediction error minimization and conscious inference. We have sensory states that come in, and we use those sensory states in order to destroy prediction free energy gradients or minimize prediction error to form posterior Bayesian beliefs, expectations about the external states. And then we use those to supply predictions about what we would sense with our actuators, with our motor plant or autonomic nervous system, where the gradients are just prediction errors. And then we just act on the world to realize those predictions or minimize those prediction errors reflexively. So this is a merely reflexive kind of what some people call active inference, based upon perceptual inference and then the subsequent action selection. And you can do lots of interesting simulations of quite complex and biomimetic behavior using those differential equations simply by writing down a generative model and then solving the equations, the gradient flow on the variation-free energy, which is just predictive coding, it's just Kalman filtering, but equipped with this ability to also act upon the data. And that ability is important because what it means is that the agent is now causing their own data. They are the author of their own sensations. They are creating changes in the outside world that supply the kind of data, the kind of sensory impressions that the agent thought was characteristic of their lived or sensed world. And you can illustrate that very simply. For example, what we've done here is give an agent a generative model that has some autonomous dynamics. You can think of this as a central pattern generator that then in this model maps to a point in extrapersonal space that is invisible and is attached with an invisible spring to the tip of the agent's finger. So as the point moves around, the agent thinks that she should see and feel her finger being pulled around. And of course, because she has the ability to realize the descending proprioceptive feelings based upon this generative model, she will move her finger and in so doing, generate the visual impressions that she predicted, basically causing her own sensorium. And this can be thought of as a very simple example of active inference generating recurrent handwriting, the letters J and A here. This is an interesting simulation because what we can do is we can actually remove the feeling, the proprioceptive prediction error, so that the agent can no longer feel herself move, but still can see the same visual input. So this would be like somebody else moving, somebody else, another person, generating the visual input. However, the agent's generative model has all the machinery that still allows the agent to predict the visual input in exactly the same way as before, and therefore when exposed to this visual input should engage via this predictive coding scheme exactly the same expectations or representations or internal states. And that's exactly what happens here. So what we have done here is plot the activity of one unit here whenever it crosses a half maximum threshold as a function of where the finger is in Euclidean or extrapersonal space. And what we see is that this synthetic neuronal population shows characteristic responses that you find in electrophysiology, say, for example, a place field response that's selective to a particular part of space, with also a direction selectivity, prefers the downstroke as opposed to the upstroke. And crucially, shows exactly the same response selectivity and receptive field characteristics under the observation of another's action in relation to when the agent is actually causing the sensations herself when actually acting. So the idea here is that this is a very simple metaphor for the mirror neuron system, illustrating how far one can get in terms of these very simple formulations of action fulfilling the predictions of a generative or a world model, all based upon this Markov blanket that itself rests upon the sparsity of influences from the point of view of a random dynamical system. I'm now going to make one simple move. I'm now going to remove the influence of action on the internal states. And why would I do that? Well, I might want to think about very big brains with lots of hierarchical structure where most of the internal states cannot see directly the active states. So I'm now moving from very simple, small brains to larger brains of the kind that you and I possess. So I'm just going to remove that. And now something very interesting happens. Now, the active states now become vicarious causes of my sensory states. But we've just said that we can always describe the internal states as representing the causes of sensations, which means that now the internal states now must be described or can be described as representing my own actions. So I have real variables that do action, but now I also represent my own action. And this produces a different kind of entity than I try to describe here just by simply removing this arrow here, moving from, say, a single cell organism to a multicellular organism, here a little mouse. And in so doing, we now have a description where we have representations not just of the external states and how they cause the sensory states, but also a representation of our own actions. And this leads to a much more interesting or richer kind of agency in which we take our original functional architecture and now equip it with an extra level where I'm now representing, I have beliefs about my own actions. And in machine learning, this is sometimes known as planning as inference, where I'm now just conditioning my beliefs about, Bayesian beliefs about external states on the current policy or action I am pursuing with prior beliefs about that plan or that policy or sequence of actions to build the best representations or beliefs about states of affairs that then can be used to predict the next thing that I am going to do. So my reflexes now are going to fulfill plans. So what would explain how mathematically, what am I going to believe about my own action? Well, if I am the kind of thing that has attracting sets of states and preserve my Markov blanket, then I must be minimizing my free energy. Therefore, my actions, my plans that minimize free energy are going to be the ones that are most likely. The free energy expected, conditioned, or given a particular plan or action. And we can write that down in terms of something called the expected free energy, which is one of the key things that active inference brings to the table in terms of planning. So what I've done here is just, if you don't understand the maths, don't worry about this. I'm using these equations illustratively just to show the nice symmetry or relationship between what we're trying to do in the moment when we're trying to minimize surprise, free energy, or prediction error, and what the same kind of thing looks like when we roll out into the future when asking, is this policy, is this plan a good plan? Does it minimize my expected or future free energy? So here's the free energy functional written out in full. If I was a statistician, I would interpret it in terms of complexity minus accuracy, meaning that I am always in search of accurate explanations for my sensations that are as simple as possible in accord with Occam's principle. If I was in machine learning, this will be known as an evidence lower bound, or upper bound in this instance, simply because the surprise or self-information is just the log evidence, and the remainder of the free energy is a KR divergence that has to be, that can never be less than 0. And in this instance, the divergence is just between my beliefs about external states and the true posterior density over the external states, given my sensory information. Now, here's the interesting bit. What would happen if now I didn't have the sensory states because they were in the future and they were conditioned upon a particular action? So now I have to take an average under technically a posterior predictive density over the sensory consequences of my action. And this is the expected free energy. And the expected complexity becomes risk, and the expected inaccuracy becomes ambiguity. The expected divergence becomes an intrinsic value, and the expected log evidence becomes an extrinsic value. So what do I mean by intrinsic and extrinsic value? These quantities, some of you will be very familiar with. Let's just ignore extrinsic value for the moment, just the the surprise, sorry, the log probability, which is the value that we spoke about right at the beginning of the presentation. Let's just ignore that. Everything is equally plausible. I am happy with any sensory state. So what are we left with? Well, we're left with this intrinsic value that is simply the expected information gain. It's in the visual search literature, it's known as Bayesian surprise. It's just an expected divergence, difference between my beliefs about the outside world with versus without the sensory consequences of a particular action. It's how much information I would gain if I did that. Another way of looking at this is the reduction in uncertainty about states of the world that would ensue if I committed to this action. Another way of looking at this is just the mutual information between the external causes and the sensory consequences that would afford itself if I pursued this particular policy or action here. So you can read this as, if you like, expected information gain, epistemic affordance, reflecting the value of information, underwriting exploration. What I'm going to do now is take another kind of uncertainty out of the equation by assuming that there's no ambiguity. I'm assuming that I can see everything, that my sensory states are basically the external states. And if I do that, I'm just left with the risk. What is the risk? Well, it's another KL divergence. In this instance, I need to now minimize the difference between what I anticipate will happen if I do a particular action A relative to my prior beliefs about the external states or the sensory consequences, those states that I find attractive. So I'm trying to minimize the discrepancy, the divergence between what I anticipate will happen and what I prefer a priori to happen, where my preferences are just a description of the states to which I am attracted. So this in engineering is known as KL control. In economics, you can read this as risk sensitive control. So I am going to make now a final move and take all uncertainty away, including the ambiguity and any resolvable uncertainty. So now I know everything that I can know about this world, and I'm now just left with the extrinsic value. And as we have established, this is just the log probability of my attractive states. It is the value, it is the expected value, in exactly the spirit of expected utility theory in economics. So let me close now with an example of a simulation, a numerical study using the expected free energy, and with a focus on this intrinsic value, this epistemic affordance, this expected information gain, demonstrated in the context of acting or planning to move my eyes. So let us assume that I can only see a very small part of the visual scene in terms of, say, a foveal representation. And I have some hypothesis that the visual scene is caused by this external cause. What this expected free energy, and particularly the intrinsic value, scores is the information gain or the resolution of uncertainty I would get if I looked over here, as opposed to looking over here, as opposed to looking over here. And if I evaluate that expected free energy, which you can think of as salience, as at every point that I could actively move my eyes, I can create a salience map. And indeed, that kind of salience map looks as if it does attract real eye movements or explain the eye movements of real people. This is from the classic work of Yarbus. We can simulate this kind of thing. Here's a very simple example. This agent thinks that it lives in a very simple world where she could be looking at an upright face, a sideways face, or an inverted face, but can only see very small parts of the image at any one time, and has to plan carefully where to look next to minimize her uncertainty about the state of the external state, this one versus this one versus this one. So here is what the agent actually sees with a sequence of eye movements denoted by the red dots here and in movie form over here. The salience maps change as we move through time because they are a reflection of what the agent believes at the moment that depends upon her previous epistemic exploration or epistemic foraging, driven by trying to minimize or choosing those actions that minimize expected free energy. And here are the samples, and here are the posterior beliefs, demonstrating that progressively, as evidence is accumulated through this epistemic foraging, there is a confident belief that she is correctly looking at the upright face. So that's the final demonstration. I'm going to give the last word back to Helmholtz, who summarized everything I've just said in the past 20 minutes expertly, as always, with the following quote: "Each movement we make by which we alter the appearance of objects should be thought of as an experiment designed to test whether we have understood correctly the invariant relations of the phenomena before us, that is, their existence in definite spatial relations." And with that, all that remains is for me to thank those people whose ideas I've been talking about, and of course to thank you for your attention. Thank you very much indeed.
Thanks very much, Professor Friston, for a very systematic and comprehensive introduction to the idea that governs any complex adaptive self-organizing system interacting with the environment. I can see this is a very unifying kind of framework in addressing a complex system when the system is it can be delineated from the environment. And I think you made a very clear case about starting from the concept of Markov blanket and so forth. And this almost makes it a necessity for this system to work according to these principles that you outlined. So the next 20 or 30 minutes is going to be open question and answering from the panelists as well as possibly from the audience. So I'm going to start with a question which, when I first read about that theory, the proposal of using free energy as something to unify both the living and non-living system, I just felt, wow, this is just truly a remarkable attempt or a theory, because we know that, so first, when one tried to look at the physical system and the information system, of course, the entropy first come in as something that bridges the two parts. You have both have the thermodynamical, physical entropy, as well as information Shannon entropy. Now you have the free energy, which can also seem to bridge across the physical realm and the cognitive, the living things realm. And clearly there's implications for that. So in order to make this truly a framework for describing living systems, I'm wondering, my first question is that, would you also map the concept of work and heat, which are the physical concepts, well defined, and people know how it operates in the physical system, to that of a living system? Like, what is heat, or what constitutes heat, or what constitutes work in terms of the system interacting with the environment? And that's number one. And the second question is that, if so, then how would you delineate or even separate the physical heat or physical work that the system does to the environment and this informational heat and informational work that the system is doing to the environment? So I want you to kind of share us with your views on this particular question, the burning question of mine. Thank you.
Yes, that's an excellent question, and literally a burning question thermodynamically. There are a number of deep points of contact between the free energy principle as a purely information theoretic description of dynamical systems and thermodynamics and sort of entropy as read in terms of James's maximum entropy principle in terms of the physics of measurement. So the free energy principle can be regarded as dual to a constrained maximum entropy principle of James, where the constraints are afforded by the Lagrangian or the surprise or the self-information, namely by the generative model. So provided I stay in my attracting, if I am constrained to remain in my attracting set, then I'm going to maximize my entropy in exactly the same way that James formulated the physics of measurement and observation. Notice that the entropy here is the entropy of the measurement or the belief. It's not the entropy of the thing that you are actually measuring. I think, though, your question speaks to a more pragmatic issue. What is the link between the thermodynamic work done by a Bayesian machine and the belief updating? And of course, you will be asking from the point of view of the information geometry. So I'm going to give you an answer which possibly only you will understand, but I think it's an important answer. So what one normally does is think about the process of self-evidencing or active inference as movement on a statistical manifold that has an information geometry. So the information length scores now the degree of belief updating, and that in itself can be associated via Landauer's principle, or more specifically the Jansky equality, with the amount of thermodynamic work required to move on the statistical manifold. So that means that in order to update my beliefs, I have to erase information, I have to move on that statistical manifold. There's a well-defined metric on that manifold that interestingly relates to the confidence or the precision of my beliefs. But crucially, it has a thermodynamic cost. So for every time I change my mind to a certain extent by moving on that manifold, then I will have to do some thermodynamic work. And that means you can now, I think, roughly interpret the thermodynamic work or heat production as monotonically related to the degree of belief updating in our brain. And that's certainly how I now think about brain imaging. So I now think about brain imaging, certainly fMRI, as just a measure the amount of heat that's been generated, the thermodynamic work that is being done, that tells you how much belief updating is going on. And interestingly, because that the measurement of the distance in the information geometry depends upon the precision that psychologically can be read as confidence or attentional gain. It's also a way of thermodynamically measuring the belief updating to which I'm currently attending. So I think there's a very direct link between the thermodynamic physics of neuronal dynamics and this formulation of Bayesian mechanics in an information geometry. The second reason I think it's really important is when you come to try to emulate this kind of Bayes optimality or Bayesian mechanics in silico or in artificial intelligence. So now the drive would be to get down to that Landauer limit to do the most efficient complexity minimizing belief updating that you can, which would be just to do it using the by minimizing the free energy or the prediction errors. The slight problem that we have, or that people have, I think, currently in computer science, is the fact you're working on a von Neumann architecture where you have to read things into memory, and that now puts you a long, long way away from the Landauer limit. So there's I think it has real practical implications. If you want more biomimetic artificial intelligence, you're going to have to elude the Van Neumann bottleneck or the memory wall, which of course speaks to potential excitement about photonics, quantum computation in memory processing. So that's, I think, a really practical example of where the information geometry couples to the thermodynamics through Landauer's principle that actually makes a real difference in terms of where you would invest in trying to emulate general intelligence.
Well, thanks. Thank you very much for also mentioning the Landauer limit, the link, the possible link between the physical world and the subjective hour and the mind and so. So the next one is also on our panelist, Mr. Zhenquan Zhang.
Yes, thank you. And hello, Professor. Thank you for your excellent presentation. And since I'm not majoring in math or physics, so my question is may more about the inspirations of FEP on deep learning. So we know that like to give the best explanations of its sensory input, and FEP-based agents should gather information to reduce the uncertainty of the environment state and the parameters and the structure of its internal model. So because that the causal graph is also a structured model to describe the environment and rely on the interaction with the environment or interventions in causality literature to gain more information about the model structure. So my question is, how is the structured learning and the free energy principle, and how does it related to the intervention data causal discovery or causal representations?
Yes, another excellent question. Yes, there is a very close relationship between structure learning, causal discovery, network discovery, Bayesian model selection. So most of our conversation today has just been about inference about states, but you also have to infer and update the parameters of a generative model if you're in deep learning, these with the connection weights. But what you're saying, also the very structure itself has to be optimized in relation to the marginal likelihood or the variational bands, such as free energy or equivalent of the elbow. So you can apply exactly the same objective function to the problem of structural learning in two ways. So I like to think of this in terms of there's a top-down approach and there's a bottom-up approach. The top-down approach is you start off with a structure that is overly parameterized and too expressive, and then you remove redundant components to see if the elbow increases. So this would be from a statistical point of view, it would be Bayesian model selection by reducing a model. And what can happen usually if you remove a redundant component from an overly parameterized model, then the marginal likelihood or the elbow or the model evidence will increase because you're minimizing the complexity without changing the accuracy very much. And of course, the evidence is equal to the complexity, the accuracy minus the complexity. So you just use straightforward Bayesian model selection using the variational free energy to carefully prune a model by removing component by component until the free energy stops increasing or the model evidence stops decreasing. That will be Bayesian model reduction. There's a Wikipedia description of that. And I suspect that's how we work in terms of evolution. So you can also look at natural selection and evolution as an instance of this kind of Bayesian model selection, but also from the point of view of neurodevelopment, we are equipped with very, very big brains in relation to our bodies. And we spend the first 10 to 20 years of our life pruning away all the redundant connections. So you could say that we are born with an overly expressive generative model, not too overly expressive, but in the right way to be pruned, that is now fit for purpose for our econish at this point in evolution. I'd also suggest that machine learning uses this approach. It starts off with overly parameterized models and then tries to reduce and prune them down to create a foundation model, if you like. However, there is another approach, and that's the bottom-up approach. So you can think about growing a model from scratch. And the way that you would use the Bayesian model selection or the free energy here is that whenever you get a new piece of information, If you assign it its own latent cause and evaluate the expected free energy of the marginal likelihood or model evidence of the new model relative to the model without equipping it with a new component, say hierarchical level or state or node in a graphical model. If the model evidence increases in relation to a model where you don't grow the model, then you accept the growth, and then you get the next bit of data, and then you repeat the process, slowly ingesting and growing the model, but only when the model evidence increases when the new data comes in. So this is a kind of structured learning where you're slowly growing the model by selectively ingesting data. And you can look at this a little bit like Maxwell's demon. If the data are very informative and they cause the model to grow, then you let the data in and you assimilate that data as scored by the integral. Well, it's the expected free energy, which is it's sort of equivalent to a constrained mutual information of the kind you'd find in machine learning. And then you continue that process until there is no more new novel data that will cause your model to grow, at which point you become old and wise, but minimally complex in terms of being able to explain those kinds of data.
Oh, yes, yes.
Oh.
Thank you. Thank you for your
Right,
very
thank you.
inspiring answer.
So yeah, so let's go back to Professor Jiang Zhang. I think
Okay. Can you hear me? Can you hear me?
Yeah.
Okay, thank you. Thank you, Professor Friston. You give us a very nice talk. And I have a question that is, it is very exciting if we can use a unified view to model living and non-living systems. However, my problem is when we just given the observational data, how can we distinguish between living and non-living things? Thank you.
Yeah, wonderful question. And I think also speaks to a part of Professor Zhang's original question. I think what you're asking is, clearly there is only one free energy principle, but it can be applied. And so I should just say, I regard the free energy principle, it's just a method, it's just a tool. It's a principle in physics is just a tool. So it is just a principle of least action. But you can apply it to different kinds of things and different kinds of generative models. And I think your question is, what would be the way in which you would distinguish between living and non-living? And I think the answer is very simple. And I don't know, but I'm hoping that my colleague and part mentor Ping O is online. And what he would say is that you have to have a preponderance of this conservative divergence-free solenoidal dynamics in play. So you have to have life cycles. If you remember before, we were decomposing, and I illustrated using a simple version of more complex decompositions, using the Helmholtz decomposition into sort of dissipative and non-dissipative or conservative solenoidal flow. That solenoidal part, I think, is definitive of biotic or biological self-organization. And what it means is you'd expect to see a certain recurrence or cyclic aspect to a living organism. And of course, that can range from oscillations in my fast gamma oscillations in my brain through to respiratory cycles and biorhythms, right through to life cycles. So you have to, unlike a stone or unlike an inanimate or sessile thing, you have to have this itinerancy that inherits from the solenoidal part of the dynamics. And furthermore, that would entail a breaking of detailed balance. And one could also argue, as some people do, this is the definition of the difference between a non-equilibrium steady state and an equilibrium steady state, the very presence of what Ping sometimes describes as the Red Queen dynamics in evolution. So I think that would be mathematically the bright line that you would use to distinguish between living things and non-living things, would be the presence of, first of all, motion. You have to have active states to move, but even within that, even within the setting of particles that have active states. I think you'd be looking for evidence of this conservative solenoidal dynamics. And then the next step is, do they actually do planning as inference? So do they have a generative model that moves into the future? That there is probably the it is probably the attribute of large things or multicellular things within internal Markov blankets, where the deeper internal states have become divorced or sequestered from the active states, so that they start now modeling the active states, and they then acquire this ability to plan. So you can look at sort of, you know, going from a small stone through to a virus that has some kind of life cycle, through to an animal, right up to things like us that can possibly look very, very deep into the future.
Okay, thank you.
Okay, thanks. So the next question is one that that was submitted by an audience who read your work and who submitted a written question for us to pose here. He is a physicist, and he would like to ask, he says, and I'll read, while steady state distributions are characteristic of Markov processes, the master equation matrix also involves other eigenvectors and eigenvalues to describe the properties like system response. So we'd like to know, are there any discussions in current theory about response characteristics of the system in response to the external stimulation, in particularly in terms of the frequency response characteristics? So he would like to ask that question.
Yeah, well, I mean, I think every neuroscientist would say, yes, that is absolutely true. And, you know, in a sense, all that we spend our lives doing empirically is pinging the system and looking at the response in terms of the implicit transfer functions, for example, event-related potentials in electrophysiology, fMRI, having even through things like game theory, psychophysics and the like, they're all predicated on the response of a particular brain or person or system to informative perturbations that just reveal the impulse response, the nonlinearities that are requisite for the solenoidal flow that we were talking about before, render those responses context sensitive. And of course, that's the basis of good experimental design. You provide the same stimulus in different contexts, whether it's an attentional one or so you're exactly trying to get a handle on the nonlinearity of the dynamics that underlie these context sensitive effectively impulse response functions. Of course, from the point of view of physics of self-organization, there's a certain kind of itinerancy that's brought to the table when dealing with non-equilibrium systems, or systems that have a non-equilibrium solution. So not only do you have that context sensitivity, but you also have you have to be careful that you're eliciting the same responses in the same part of phase space, because of you could have wandered, for example, performing an ERP study on me when I am asleep as opposed to when I'm awake will give you very different results. So there's an extra degree of complication, I think, afforded by the fact that you are dealing with very complicated biotic kinds of self-organization.
All right, thank you very much. So now let's just recognize maybe one or two questions from the audience who have attended your talk in the past hour. So I'm reading through the chat, the online chats that people post there, and there are some comments and some questions coming up. Let's see. I know Professor Aoping is here in the audience. Would you want to raise some? I saw you have posted some comments there. Would you like to make any comments?
Yeah, can you hear me?
Yes,
Yeah,
we can.
It's very good. Good morning, Carl. This evening here. Yeah, I think everything what Carl said on the physics, biology, and the neurology side, I'm completely agree with. That's excellent. The comment I want to make is that the decomposition, the Helmholtz decomposition, actually is not good enough for the current purpose. So the slides part you put on this gamma and Q, I think that is extension of what the original Helmholtz decomposition. So that's more than what the Helmholtz say. That's my first point. Second point is that even then, as recent as 2 days ago, some physicists told me they won't believe that decomposition is possible. So I think those physicists on that point to me is completely wrong. So I think it's what you are using here is first more than Helmholtz decomposition, and the second that decomposition is a gamma and Q is very general. So it's basically my comment here. Yeah, and I know even maybe I can come back with a comment to Jun, to Professor Zhang. That's also related to the decomposition. By that decomposition, there's another quantity I think Carl have not been explicit about, which is for the process, there will be a quantity like Hamiltonian or energy. So with that quantity as Hamiltonian or energy, and then one can have a complete equivalence of to what thermodynamics on the heat and the work. So with the effective Hamiltonian with that one can define the work in this situation. So that may come back to Professor Zhang's question. So one can indeed do this even on the exact mathematical level.
Okay, so Carl, do you have any comments about the decomposition? I think that was the first part of this one. About decomposition.
Yes, well, yeah. Just to beg your apologies, I'm using sort of sometimes simplifying the maths for presentation purposes. But just to put Professor Eoping's comments in perspective, in fact, one of the very first, I think, formal formulations of what I've been talking about was very early on in a joint paper with myself and him entitled Free Energy, Attractors and Value. So it'd be interesting to go back to that and see how much things have changed over the past 10 to 20 years. It's
all right. Thank you for making that historical comments, the comment on the historical perspective on how things, ideas evolve throughout times. So we will have time probably for one last question, if you don't mind, Professor Friston, which is from one of the audience, Richard Tong. Are you there? Richard Tong, you made a few comments. If you might want to just turn on your video and just share your question. Richard Tong.
Yes, thank you for giving me the time. And I have actually several questions, and I think I probably will just focusing on one of them, which is talking about the implementation aspect of the free energy principle in the field, right? So there's I think in my first question is that there's the kind of like the critique or some of the debate on whether FEP is suitable to be implemented and transfer that principle into implementations in the machine learning, especially deep learning field. And there's the kind of like opinion of different type of approach, and one of the critique is to say how if FEP is not unfalsifiable, how could it be then used and then validated, especially when we're implementing systems using this approach, right? So that's and also to more specific implementation approach, like for example, when we're talking about Bosman's Boltzmann's machine, that Hinton is proposing, and also the JIPA that is proposed by Young LeCun and so forth, use a lot of the free energy also principles. And what is your opinion and suggestion on kind of like converging or integrating this type of approach based on the same principle?
Good. Two excellent questions again. So in response to the first one, the free energy principle is not falsifiable, therefore is it useful? The response to that question is usually what I said a few minutes ago, that the free energy principle is just a principle of least action, and therefore it's a method. It's not a theory. It's not a beautiful idea. It's just a principle of least action that you may or may not apply. It's up to you. So you can apply, if you want to create or reproduce in silico Bayesian mechanics or inference or active learning or structure learning, then you can apply the free energy principle. And in principle, that will be the most efficient way of doing it, in virtue of the fact it is a principle of least action. And that by efficient, I'm now appealing to the information theoretic criteria of efficiency, which means that you can certainly apply it in a deep learning context. The question then is, at what point would you apply it? And normally, what happens is, you first of all, how do you identify the right generative model? So the free energy principle, a bit like the principle of natural selection, for example. Well, that's actually a theory, but the principle of one of the principles of natural selection. It doesn't tell you how to do it. It doesn't do all the heavy lifting for you. You've still got to do all the hard work. And that hard work is identifying the right kind of generative model to reproduce the kind of learning or behavior or choice under uncertainty that you want to reproduce and or study. What the free energy principle does is tell you, well, once you've got your generative model, you can update it and you can use it for inference and learning in the optimal way, but it doesn't give you the generative model in the first place. So I think that's worth stating. In response to the question, which I think is an excellent question, is there any convergence between people in machine learning and the more biomimetic approaches that would inherit from a commitment to something like the free energy principle as applied to biotic self-organization? I think there is. I look at Yann LeCun as one of the most important figures in that space. I regard him as like a partner in crime, arguing against many of the less principled approaches that you find in machine learning. And certainly the JEPA, or certainly the architecture he's bringing to the table, is extremely consistent with the kind of architectures you'd expect from generative models that would emerge under the application of the free energy principle. And indeed, technically, they're formally identical. There is a slight twist for your entertainment. Sometimes Yann says things that seem inconsistent with what people like me say, but that's not quite true. So he has a particular view of what generative AI means, and it's not the same as a generative model. So when he says it's not generative, he's not saying that it's not important to have the right generative model. The other interesting twist is that he deals with a zero temperature free energy. And in zeroing out the free energy, he removes the uncertainty from the problem, which means that he is on the positive side now free to use standard maximum likelihood techniques in machine learning. But on the negative side, you run into all the problems that people in machine learning contend with, which is overfitting and all sorts of sort of hyperparameter tunings to elude the overfitting. The overfitting problem and the sharp minima that attends deep learning is simply due to the fact that the objective function does not include the uncertainty in accord with the free energy principle or James's maximum entry principle. And that's and if the temperature scales the uncertainty or the entropy, then a zero temperature free energy is exposing yourself to dealing with uncertainty in the right kind of way. So I regard Jan LeCun as traveling in exactly the same convergent direction as me and my community, but with a slight twist. He's got to go from t equals 0 to t equals 1, and then everybody will be happy.
Thank you so much. Really appreciate the answers. Yeah.
Okay, with that, I think this is a good time to conclude our the portion of question and answer, as well as the presentations. I'll turn this over to Ms. Liang Jing for the next phase. Yes.
Okay. Thank you, Professor Friston. It's really wonderful. I'll show the slide and show the cover of the book, Active Inference. It's really a wonderful talk today, and we learned a lot. Sorry. Can everyone see the cover of the book?
So the
actually,
Chinese,
the Chinese version
just become available. Yes.
Yeah. Congratulations! And so all of our members from the study group could read the Chinese version and learn a lot. I think maybe that's all for today's talk. If people have more questions, we could talk about it later in our study group. So thanks for Karl today.
Well, thank you very much. It's been wonderful speaking to you, and thank you for the picture of the book. It looks prettier than the Western version.
Thank you very
for
much
the publication.
Nice having you here.
Maybe we could take a screen photo.
Yes. Yeah, people turn on their video so we can take a screenshot.
Yeah. Please, everyone, please turn on your camera if possible. Cool. I took several photos and I will send it to you by email.
And also the second pages, the second, third pages, I think there are more faces coming up. So you want to take everything. Yeah. All right. So thank you, Professor Friston. And then we are going to have, I think, a small break, right? Is it according to our plan? So we're going to have a small break. And in 5 more minutes, we're going to come back. And we're going to rework on this theory, this time in Chinese. So hopefully we are able to digest all the highly information-packed session. So we are going to study the theory very, very much. Thank you very much. Okay.
Thank you.
So,
好，大家好，我们接下来进入圆桌讨论的环节。就圆桌嘉宾，首先介绍一下首先是张俊老师，张俊老师是上海数学与交叉学科研究院的教授，以及第2位是汤雷汉老师，汤雷汉老师是西湖大学统计物理与复杂系统实验室的教授，然后以及张江老师是北京师范大学系统科学院教授，是极致俱乐部的创始人。然后后面是我是北京师范大学系统科学院的在读博士生某慕云以及张正全是复旦大学信息科学与技术学院的在读博士生。那接下来的部分是我们围绕下面的一个话题进行讨论。需要翻一下页。对，就是我们圆桌讨论的话题是上面4个话题。首先第一个是主动推理的 high road 数学物理相关问题进行讨论。第2块我们会围绕自由能原理如何帮助我们理解认知、心理、意识、行为和生命这些概念去进行讨论，以及其中包含一些自指、自创生以及自组织这样的一些概念。以及第3块是关于自由能原理和强化学习相结合，以及和AGI 就是通用人工智能相关的讨论，就是包括自由能原理相比于强化学习有哪些优势，对强化学习有哪些启发，以及自由能原理是否可以帮助我们实现更好的 AGI 或者 ASI。最后一块是自由能原理它所面临的一些挑战，以及有哪些待解决的问题。对，然后接下来就可以各位嘉宾是 可以自由的进行发言讨论。
我们可以大体按照这个问题，要不然先从第一个问题开始讨论吧，因为大家对物理方面好像就是问题比较多。
是可以直接问吗？还是有一个顺序？
这应该就是直接进行开放性的讨论，就是不用设计很详细的顺序。
对对。
好，那我想问一个问题，就是刚刚想问，然后没有来得及，就是我在看这个自由能原理的时候，首先从马可夫坦这个概念就可以看出它有一个局域性的一个性质，然后呢，然后你再看它这个自由能原理它有两个方式来最小化自由能，一个是改变一个系统它自己的信念，另一个就是说你去改变外界世界。那么这两个方式，它其实有个对称性，它就很像一个弹簧。然后所以我有一个问题就是，这个自由能原理，如果你把它放在一个连续的空间上去看，把它放在场论的框架下。它似乎很像波动方程，但是我们又从另一个直觉上就知道，波动方程它和智能和生命又是不完全一样的，所以我的第一个问题就是，呃，自由能原理和波动方程它有什么关系，有什么差别？然后另一个进一步的就是说，你从这个角度来看的话，波动方程它在微观上面你可以有一个写出一个方程，然后你在宏观上面也能够观察到一个现象。那么进一步的问题就是，自由能原理，你如果在微观尺度上面看到一个系统它符合自由能原理，那我们能够说它在宏观尺度上也有相似的原理吗？还是说它是限定在某一些特定的尺度上的？好，谢谢。
对于前一块问题比较偏物理，就是有没有物理领域的老师和同学可以回答？
那个我可以回答吗？
可以，这是比较开放的提问，就大家都可以自由的讨
对，
论。
那个同学，这个问题这些问题提的非常好。呃，第一个问题，答案比较简单，就是自由的原理背后用到的动力学，跟波动方程完全不一样，要牢记这一点，完全不一样。就是说你如果学过那个数学物理的话，波动方程是一种双曲方程，自由论原理背后的东西必须要涉及一部分，是个椭圆方程，所以完全不一样。所以你提这个问题回答就是说对你的那个期望是个否定的回答，不一样。但是呢，它们都是整体的，描述整个空间。不知道这个。然后第二点就是说这些差别。那么我大概有五六年前吧，写了一个书评，那那个书评论这个评论商，所以就特别把后面的这些大家容易混淆的地方，我觉得讲了一下，特别是里面有几个点，我觉得在中国是尤其的误解，就是热力学熵这个东西。我以前就说我一个书评就评论这一点，所以可以去看看。当然你可以不认同，我们下来可以继续讨论。
谢谢。我对这个椭圆方程还不是特别了解，我可以回去再看一看。
可以这么说一下，就是椭圆双曲方程的话，实际上是能量它里面有个守恒量，这就是通常意味着是，比如说能量守恒。椭圆方程的话，实际上是不守恒的，里面涉及到扩散的各种东西。所以刚才你也看见这个Karl Friston用的那些量，比如说那个伽马，那算是描述扩散，所以它是一种椭圆形的。
那有可能把它的那个自由能原理，看作一个就是不用那种波动方程，而是用别的方程，就是形成一种一个场，就是它里面的每个点，它就是一种场论形式的自由能原理，这有可能吗？
这是可以的。就是说你要扩充大家通常对这个，这是我的理解。我们也做过一些相关的事情，就是说你可以扩充通常这个标准那种守恒性常论这种做法，这是可以的。 而且呢，我觉得在某种意义下，接下来结果那个数学结构就很接近于张俊老师一直在推动的一种，就是说他一种特别的几何学在后边。但是我觉得我在国内还没见到人在明显的讨论这个事情，我只看见就是说，这是也是张军老师自己告诉我的，就做一些相关的它里面有些我觉得有些新的几何，怎么叫我不知道，所以也许我们这儿呢有很厉害的年轻人，把你们那些数学结构会把它解析得很清楚。
好，谢谢谢谢，这个非常有意思。
就刚刚
那
讲的
那我
那个，就刚刚讲，我想评论一下，就是刚刚讲那个，你说想把自由能原理写成像一个场论的这个形式，对吧？这个你在物理系统里面，这个倒是有可能，我觉得，但在那个神经系统里面，在脑的计算理论里面的话，因为它这个神经元对神经元的连接，它都是很特定的，所以它不是以一个场的形式在传播的。所以呢，因为它这个所有的功能区域它都是很特定的，所以呢，这个就可能不一定完全像这样，但是我也听到有相反的表述，或者有一位还是相当著名的一个计算神经生物学家告诉我，他现在相信可能大脑的这个工作机制的话是通过这种所谓叫 law of mass action，就是说是按照基本上像场论这种形式要来刻画的。所以这一点的话，就是你刚才提的问题还是有意义的。但是我再回到开始的时候，我就是转述了一个问题，事实上是那个汤雷汉老师他没有赶得及，现在上来了，汤雷汉现在上来了，就是说关于本来要想问那个 Friston 关于那个响应这个问题，对吧？你想那个频率响应这个问题，那么他这个。可能是我这个问题问的不是太好、太明白，让他使得知道他可能想要回答什么。但是他一直在，就是 Friesen 一直在研究大脑的这个，当然脑成像的这个方面他很熟悉。另外呢，他也在研究像那个脑电波这一块，对吧？脑电波的话呢，就是当然是完全是一个功率频率的一个曲线了，对吧？所以说我就不知道从雷汉角度来讲的话，你讲的那个响应的话是什么意义下的响应？所以现在雷汉上来了，你可以介绍一下吗？
各位好，非常抱歉，今天飞机晚点了，本来我想可能大部分能听到，结果又晚点了差不多1个小时，所以非常抱歉没有参加报告那部分，还有当场问Karl问题。我觉得他讲的至少我听的那部分，听到最后一个尾巴，我觉得还是很有意思的。当然实际上我的个人的看法就是整个这个问题实际上是很复杂的，还有很多侧面。特别是跟这种现在的机器学习，它到底什么关系？我实际上有一个基本的问题，刚才张军也讲了，就是因为他本来我在网上看他的报告呢，他把它完全看成一个动态的一个非平衡态系统，那么写一个主方程或者 Fortran 方程，然后他得到，然后他有Markov 什么shell 还是什么。边界，然后他说可以推导出一些关系，但是呢，实际上我一直不清楚他这个动力学，他这个时间呢到底是什么意思？实际上你像 neural network，他训练好了以后，他也没啥时间，但是呢，当然你每次给他样品的话，他会给个答案或者是怎么样，你就根据你的这个训练的时候不同的要求。另外就是如果是因为通常我们讲的分布是data 的分布，对吧？就是你data 它有一个分布，然后呢训练到 neural network， 然后 neural network 它实际上是 make a copy of the distribution of the data， 尽量呢和至少某些 feature 它是描述的比较好，但这个本身实际上你做完以后，分布已经在那了，它没有什么动力学 actually， 所以也许它没有关心那些我们通常觉得非平衡态稳态的那些动力学，实际上它可能只是关心分布，因为你的 neural network 训练好了，它那些 states 或者什么，所以它这个 formulation 我觉得有点这种 ambiguity 在那，它没有讲得很清楚。这并不是说它的一些思路或者一些结论真的有 不成立或者什么。但是呢，我觉得至少对我来说，我想把它搞得更清楚一点，他到底是在想说什么。他有很多 intuition， 刚才张军也讲了，他就比方说 neuroscience 出身的，那么他的一些想法，包括一些实验观察，都是他这套理论好像也是可以在某种意义上，但是我的问题就是说，这种某种意义是什么定义，什么意义？所以这个我觉得我们有这个讨论班非常好，这是我的一点看法。我只是主要是些问题，并没有什么特别的答案。对，谢谢。
我雷汉，我觉得只要你写下方程，你就知道是怎么回事了。就是这种空对空的讨论，通常是不清楚的。
对啊，就是他没有方程，我没有看到他有方程。他就说他是 for plan， 但是
他
他如
有了方程，
果真的是一个，
就只有在那个空的方程上面，比如说讲 hem 或者 decomposition，除了我以外，好像听众人没有或者别人没
但是
有人问
可能有
这些问题。
另外我们在座的其他人可能真的仔细研究过他的工作。那么我们是讨论嘛，我只是提出一点问题，供大家参考。
还有就是那个稳态，可以是动态稳态，就不一定是点状稳态。所以换句话说，他写的这些东西，它可以是动态的。
但他的时间他没有，
如果是
真正
动态的，
都
其实稳态都有时间。
他是研究一个什么样的？因为他不能说你这个大脑，比方说他是说我大脑正常，那不断的有那种刺激呢，还是说你每次大脑somehow有个状态，然后你每次信号进来，然后它有个响应或者超前预测，对吧？That's all possible。但是呢，那个是说他那个稳态是什么意思？是说我这个大脑没有外面刺激的时候那个状态呢，还是什么有刺激的状态？还是我根本没有任何 idea。
没有，你两个都是，两个都是。
那你不可能两个都是。
你不刺激你大脑就有一个动态稳态，这是实验上观察到的。
但是也不是你，那我睡觉的时候，或者我
对，你睡觉的时候
内部也有很多 process，
你这个脑波都在动。
对，但是呢，他不可能，我不相信他的理论伟大到把我任何时刻的这个，我突然有个想法，对吧？他突然冒出来的或者什么，甚至有人相信有那种，那叫什么，这种意识或者是一种，
对，比如说那个
对呀，
meditation，
突然突发奇想那种。
对，
那他是在稳态里面还是不在稳态里面？我觉得这个有点扯大了一点，就是我觉得应该比较 focus 讨论，他到底是在想说什么，我不是特别清楚。
那我今天就是很遗憾，就是同学没有问的关于跟意识的关系啊，他这个理论的话，就跟意识，还有包括张江老师以前也提过，这关于跟自我的关系，就是自我和意识这两个关系，大家没有就是让他在这个方面谈他的看法。
对，我开始想问这个问题，就是跟那个就是这个自指啊，包括那个自我意识啊这块的，但是它实际上它这个部分里面有一块就是讨论了这个问题啊，就是它相当于是说，当那个他观察到那个就是 input 这一部分，如果包含了他自己的 action，它实际上就是这里面就包含对自我的建模，然后这个建模的过程，如果再给它就是增加它的那个 hierarchy。然后多个层次往里去走，大概他就想说这样就有了一个这个自我意识的这种感觉啊，我觉得他应该是这个意思。
那这样的话，就它的本质是在讲的话，就是说你动物体或者智能体，它在要做一个动作的，就是action planning 这个时候的话，它会往那个这个就是 effector 它的那个效用器的话。它就是传一个命令过去，同时呢，它也会传一个这个 inference copy，就是说把这个信息又回到它本身这个决策这个地方去。那么他认为 inference copy 可能是它的一个产生自我的一个最起码的一个东西，对吧？
对，所以我能预期到他这个回答，所以我就当时我就没有问这个问题。但是因为我自己的一个回答是，我觉得不止这些。因为什么呢？因为我感觉就是这里面，因为他也没特别详细展开讲，就是这个 word model，实际上我觉得它不仅仅是一个 state 的拷贝，它更多的是一个就是类似于同态或者同构，就是它把那个现实世界也好，就是它的那个动力学也要含在这个 word model 里面。所以这样的话，当你有多个这个 hierarchical 这样一个尺度的时候，它实际上是每一个尺度 它和上一个尺度都会有一种自相似性，所以这就导致另外一个挺大的一个问题，就是说这个临界现象，包括这个重整化群和它这个东西的一个关系是什么？所以这块我自己也没有想得很清楚，但是我觉得我在这个时间问他的话，可能有点不好回答，所以就没有太展开。我觉得我们可以在这里面可以展开讨论。
就学物理的人是不是可以跟我介绍一下？就是说，自由能原理在物理这个复杂系统里面的话，它在临界点的是和和重整化和这是什么关系？
这个是什么关系？我也很想问这个问题。
这个我觉得苗斌是一个专家，但是我就稍微 offer 一个，就是比方说你看涂一海他们最近的工作，那么他就是研究学习的过程，那么实际上他最后训练出来比方说你训练以后到一定的时候，他那个 neural network 那些 weights， 因为你的 weight 那个参数空间是远远超过了你需要的那个维度，但是所以说你每次初始条件不一样呢 weights assignment。然后他最后得到的那个收敛的那个也是不一样的。但是呢，对于你对这个网络的要求，就比方说让阿拉伯数字什么，他们的 performance 是一样的。就它有很多其他的 redundant， 或者它像在内部那些很多它像 activation， 每个一层到下一层，它那个 node activation 函数渐渐把那些不重要的那些参数取值了，把它的影响基本上归到零了。所以说，你实际上真正参与做决策的那些参数，或者像某个 collection of these parameters， 它是只要那些搞定就行。那其他的那些你随便 set， 因为它最后对做决定不起作用，所以它基本上是这样的一个。然后呢，我觉得这个卡尔讲的这个，是不是他说那个分布是一个 ensemble， 还是说就是它到底是一个哪些东西的一个分布，都不是很清楚。
这个我觉得雷汉你进入了一个误区。
不，我假设他是 serious scientist，OK，
没有，
我们其他的讨论没什么意思。
但是你的表述你自己进入了一个误区，因为我就说，如果你讲完的话，我可以评论几句。
你说。
刚才你提到涂一海，所以涂一海就是一个人，他最近有一系列文章。在那个 deep learning AI 里边，他认为统计力学这套框架是不能适用的，统计物理，因为他觉得他做的东西好像跟标准统计物理理解不能理解他的那个数值计算，对吧？这个图样，
他说那个FDT 不成立是因为非平衡态嘛，所以这个从这个角度来讲是有点像。
FEP 它因为我不知道卡尔讲清楚没有，它既用于平衡态。也能用于非平衡态。好，这是其二，我们就回到涂一海。我知道涂一海和他的工作，他认为这个在 AI deep learning 里面统计物理这套东西不适用，他写了好几篇文章。我几年前就告诉他，我说他的分析是错的，所以我们去年也发表的文章，就针对他自己做的结果，就表明这个自由能原理这些结构，统计物理结构可以用到。AI 可以用到 deep learning 上面去。
不，他也说可以啊，他没有说不可以，他只
没有，他说的是不可以。这是他自己的 TNS 里面就这么陈述的。
Anyway，
他陈述的这个，所以你刚才讲的东西也在沿着这个思路在做。意思就是说，自由能原理。
我没有说不成，我没有说不成立，而且他也没有说不成立。
自由能原理的成立跟是否平衡态、非平衡态没有关系，它就是一个长时间动态稳态分布的这么一个结果，所以我觉得你自己进入了一个误区。
不，我可能进入，但是不是你说的这个误区。Anyway， 我们不讨论这个，我们不能讨论。
所以第二个误区就是刚才你讲的这些东西，就是这分布函数怎么来？我觉得这个卡尔原则上也回答了，如果你接受这是个Fokker-Planck equation 或者是狼传方程，这个问题还需要回答吗？这就摆在那儿了，那就是个分布函数。就是换句话说，物理的根本必须是个分布函数。所以就是这当然这也是我在10几年、20年我一直在强调的，作为物理的根本原理，必须要考虑随机性，必须要考虑概率。 所以你接受这些分布函数来源，你就不需要回答了，它就摆在那儿了。所以我知道，刚才我特别强调，特别是在中国，很多物理学家
我们不要
接受这个观点，
我们就事论事，好吧？
不是，
我那个什么苗兵，我不跟你争论，
所有的
不跟你争论，
可以用过去。
我不是跟你争，不，我跟你讲的我也不是一回事。他那个胡一海他那个篇最早的那篇，他是有时间的，但那个时间并不是真正的时间，而是说你训练的时候，你给他不断的那些 batch training， 然后一直训练他最后确实能到一定的时候，他那个 loss function 就收敛了，所以他就不需要那个梯度法，他就不会，因为噪声也是有的，他 stochastic gradient descent
非常对，不需要真正的时间，它就是一个过程，你的 time step 你就把它看成一种时间就完了，就是一个过程。
那个我
从那个过程角度讲，你
抱歉打断一下，
你需要去区分真正的时间、假的时间吗？所以你进入了一个误区，你自己进入了一个误区，说不定包括雇佣你的进入大学也进入了一个误区。
两位老师，我们因为时间有限，就是这边还有一位同学想要发表一下意见，然后我们
对
这个问题可以快速过。
就是我首先是刚刚那个我一直在这个就 Friston 那个讲座前，这个木同学就已经提问过这个哦。
好，你现在可以用你的设备了，把你的外放上。
喂。
抱歉，我们这边好像这个出问题了，我就用我自己的电脑来回答来说这件事儿。就是刚刚在那个 Friston 那个报告前就有这个木同学就已经就是我就问过他这个关于这个非平态和平态的问题。就是我其实就一直对这件事情是有疑惑的，因为只有在这个机器学习里，我们通常就是刚刚那个应该是唐老师说这个，就是我们其实是要训练到某一个平衡态之后再做这件事情。事实上它没有这个，因为在平衡态里它有这个时间那个平移对称性，或者说叫时间繁衍对称性都是有的。可是显然在这个人脑的系统里
对不起，我要打断你一下，真是误区。这个自由的原理已经告诉你，你不需要去区分平衡和非平衡。
敖丙，你听
平衡态和非平衡态
的问题讲完。敖丙，我觉得还是听那个同学的问题讲完。对
然后那个就是因为刚张江老师提到这个就是那个关于那个临界点这件或者临界现象这件事情，因为我本人是这个北师大这个物理系的同学，然后我有个工作是有关这个大脑临界态的一个工作，然后我们其实发现这个人脑的就是在之前所有的关于大脑临界点的这个现象的工作呢，其实都是说这个它是一种非平衡相变，就是一种类似于就是雪崩这种相变，然后它事实上就我们在传统定义相变的时候，其实是在平衡态系统做的，然后我们的工作发现这个是用 fMRI 的这个数据，我们去建模这个人的这个大脑的这个一个任务的过程和有 resting 过程，我们都去做了，然后我们发现人脑其实是处于一个平衡态的一心模型的临界点这个附近，然后这件事情其实我们一直是在跟那个就是很迷惑这件事情，因为我们按照传统的想法，我们认为人脑肯定不是一个平态，就是我之前也不相信它是一个平态，但是我们的实际结果就发现它确实是处于一个平态，然后这个我们的文章也挂在上面，然后正在投，然后就是这件事情我是觉得就和这个自由能原理这件事情就是 Friston 讲的这套是有一些关联的，因为他其实想 argue
是一致的。
对，就是也许是一致的。我想说，就是也许是一致的，就是因为我们人脑并不是一个，就是我们在那个某一个任务，比如说，或者是从一个任务到另一个任务的过程中，这个我们接收到了信息，然后或者是在这个任务过程中，我不停的接受外界的信息，这个时候其实是那个在长时间的这个平均下来，我们看到人好像是处于一个平态，然后但是如果我们把这个时间的尺度缩小，显然它是不处于平态，因为平态的定义本身就需要某种这个
时间尺度
平均，
要个时间
对，因此就是我想表达就这么一个事儿，就是也许这个事情是不矛盾的，但是我本人还不太理解。
矛盾。
这个问题我想请教一下这个物理学家，就是说据我了解的话，自由能熵啊这些概念在非平衡态它也是可以也是适用的。 就是说，那么这种情况下，比如说在那个涨落、在耗散情况下，它也是适用的。
对，
所以呢，所以就是使用自由能这个概念的话，就是说是跟大脑是不是处于平衡态、非平衡态这件事情，事实上是是一个正交的事情。那么回到那个汤雷汉讲的那个 Friston 他这个理论，就是说他自由能到底是他有没有给出方程这个事情，我的理解呢是，他这套理论的话，他给出了一个就是说这个自由能的几个表达式，就是自由能这个表达式从那个就大脑那个 predictive coding 这个角度来讲，它的自由能它有哪几个表达式？关于自由能所遵循的，当然他认为是 minimizing 自由能了，对吧？这个他认为通过 minimizing 这个就可以得出运动方程。但他从来没有就是很严肃的，就是通过这个来导出个运动方程，而且他讲运动方程的时候，他就讲另外一条东西了，他是讲那个 Fock-Planck equation，他完全讲另外一套 stochastic 什么东西，所以这里面还是有一个鸿沟在这边。对，我想补充这一点。
是的，是的。
对，那个我想我也评论这一点，这个地方，如果卡尔他说是从自然原理可能推出运动方程，那么我可以100%的肯定他肯定错了，肯定错了。但是呢，如果能从他的 Fock-Planck 或这种类似的方程能导出自然原理，那肯定是那么我认为这是正确的，而且这是应该是正确的道路，就是说正确道路是从动力学推导出平衡态，而不是相反的过程。
刚才其实我最后问他的问题就是他也这么回答的，我觉得他就是说，他说这个东西就是 principle， 它只是个 principle。他说你自己的 generative function 就是你要自己去推导自己的 generative function， 实际上就是相当于这个动态方程的话，那这个的话呢不在他这个范畴里。
各位老师，因为我们时间有限，那我们可以接下来进入到第二个话题。第二个话题是关于不好意思，稍等一下。第二个话题是，是关于就自由能原理如何帮助认知、心理、意识、行为以及生命。就大家可以围绕这块话题，发表一下各自的意见。
对，我感觉我刚刚一开始的问题，其实第二个问题跟这个自组织还是有点关系的，就是可能大家都在讨论，一开始都在讨论第一个问题，就是我第二个问题就是说这个自由能原理能不能跨尺度？比如说你在微观尺度上面，你设计一个元包自动机，它使用了自由能原理，那么比如说10个或者几百个元包自动机放在一起，还有没有在宏观尺度上的这个自由能原理？我觉得这个可能还是挺重要的，因为它不是声称这个是一个通用的一个理论嘛？那你如果要为每个尺度都设计这个原理，那这个设计就是过于人为了。但如果它能够跨尺度的自组织产生这样的东西，那就比较有意思了。
我对这个问题可以说一下，就是，在那个 Friston 他19年写的一篇叫《Free Energy Principle for Particular Physics》这篇文章中，他其实就回答了这个问题。它里面因为提出了一个马尔可夫坦的概念，然后今天在他的汇报里面也他也介绍了一个例子，就是说有很多个例子，这些例子它设计了一套机制，让这些粒子相互作用，然后形成一个马尔可夫坦。他当时把那个图像里面有很多粒子分成了4种颜色，就分别区分了内部状态、行动状态、感知状态以及外部状态。那可以看出，就是我有很多这些小粒子，它的作用构成了就是一个物体，这个物体就是由一个马尔可夫坦构成的。然后在那篇文章中，他进一步的提出了一套具体的算法，可以让这套系统从一个微观，就是微观相当于是现在有很多个小的粒子，这些粒子都是一个物体，这个物体通过它设计的那套机制交互作用之后，会形成一个更大的物体。那当很多个更大的物体再进行交互作用，那也能够通过那套机制去识别出更大的，就是去组合出更大的物体，这样就能够使得这个尺度从微观跨越到宏观。那这套其实都是符合它的那套，就是基于这种马尔可夫坦假设下的这种物体的定义。那其实就是也是这套原理其实不局限于说某个特定的尺度，它是针对理论上来说是针对任意尺度都是适用的。
我想问一下专家，因为我没有真正研究过他的工作，我只是看了他的之前的一些video。他这个因为通常比方说热力学里面自由能， 它是一个状态函数，对吧？那个状态参量呢，比方说体积啊、粒子个数啊、温度啊，那么都是一个宏观量。那么所以自由能函数通常表示成只是几个宏观的系统的宏观特性的一个函数。那么但是我看他之前那个讲那个 video 里面的 PPT， 他把自由能定义成稳态分布的对数。那么这个那稳态分布就看你如果是整个状态空间的一个分布，那么实际上是一个很微观的一个东西。所以它是不是什么时候做了这个，就是从微观，实际上跟刚才那个同学的问题是相关的，就是从微观到宏观，它到底在哪个层次在做这个讨论？它如果要讨论某个具体的 receptor，或者是某个信号最后输出的那个节点的，那么它必须有一个函数能够跟那个这种微观的状态直接相关，对吧？但是呢，但是你想象，如果大脑这种，如果它有多少个 receptor， 那么它那个状态空间是 exponential， 所以你实际上从实用角度，我不知道都怎么构建这样的一个函数。你如果做一个很简单的实验，比方说几个神经元，那有可能可以用这个原理。但是呢，你如果你说用个微观态来定义这样的一个稳态分布，然后自由能量对大脑来讲，我觉得是 impossible。所以，但是呢，它确实就是它可能就是说它里面有很多工作，我觉得是目前还没有做的。这个实际上也是很大的机会，就大家一起去研究。我觉得这个是今天讨论特别有意义。但是它目前的这个框架，我觉得是缺了很多很多细节。
那个雷他是没有做，但是不等于他原理是错的。我觉得
我没有说他错，我就是说指出来，就是说这里面有可能有很多机会嘛，但是呢，他远远没有达到
最大的机会，他就是刚才你还有很多人都指出的，他没有，我也跟他讲过，他没有真正研究一个具体的过程，就是这是他的问题所在。但是它的原理，刚才讲的怎么去定义自由能是不是状态函数，没有问题的，肯定是状态函数。至于怎么去做，那是另外一回事情。
我来回应一下那个常老问题，还有那个张安博刚才那个问题哈。我自己理解就是说，它这块应该是就是取决于那个概率分布函数，因为我们知道概率分布函数它如果比如说是状态函数，那实际上这个就是尺度其实跟这个状态就有关系。如果你是在微观去研究，那么你的状态就取为微观态，那么你这个分布就是定义在微观态上分布。那我们看一个宏观的东西的时候，实际上我们把好多的微观态给它 cos grain 变成是一个宏观的东西，然后去看宏观态上的那个状态分布。所以我觉得在不同的尺度下呢，它应该都有这个概率分布。有概率分布，可能它这个自由能原理这个东西也是同时成立的。我自己理解啊，但我也不是这方面专家，我们也是正在学。
是不是专家不知道？因为我跟卡尔写了一篇文章，那么我的理解就是刚才张江教授这个说的这样，我的理解是完全对，因为符合我们做这个事情的这个做法，就是说只要这么写都可以用，跟你在什么尺度没有关系，而且还可以跨尺度，就是说低尺度的东西最后你就用到高尺度上面去了，可以用的，没问题。
那这个会不会出现那个不同尺度下的一些冲突呢？就比如说在一个尺度下看，它那个自由能是在最小，另一个尺度下看，它自由能可能没那么小，或者说它速度没那么快，或者说甚至反。
这个完全有这个可能。
哦，
就是刚才好像不是你还是谁也提过的，这就是说换了不同尺度以后，它可能就不一定是局域的了，对吧？你如果老用局域的频率，当然就可以一直撑下去。但是如果你高层次有限制，它并不一定要取用低层次的某个最低能量态，所以它就要有个就有个优化。所以这个有可能就是说你在低层次的某个稳态，并不一定对应着另外一个层次的同样的东西，这完全可能的。
那个跨尺度的话，这个问题就是说，我觉得跨尺度它应该会同意这个在每个尺度上都有它的对应的像自由能原理这个东西，但重要的问题是在于， 假如在每个尺度上你有一个自由能原理在工作的话，那么就是说你一定要把热力学的或者其他的这一些这个量，你也得要做一个很好的解释，对吧？特别是做功和那个热这两件事情，所以这两件事情可能是联系尺度之间的那个这个关系的，因为在从力学从经典力学到那个热力学这个过渡的话，从热力学到统计物理的过渡的话，那恰恰就是说，因为热这个东西出来的话，就是因为是跨尺度，所以出来热这么一个概念了。那么，但是热这个概念在计算这个角度，从神经计算这个意象，它到底是什么样的一个含义？我们刚才好像向他也提问过这个问题，他呢是回答是侧重在于，就是说在计算的过程中，你和那个就是计算的所需要一个最低的那个消耗的能量，是多少？这个像那个Landauer limit，他就谈了这个事情，就是你要 flip 一个 bit，它最低的那个能量是多少？但这个问题本身呢，是就是说是涉及到一个计算机器的它的一个极限，对吧？但是在这个计算机器它在做的一些信息处理的过程中，你说有自由能有熵的改变，但是也有一个所谓叫它的那个热量这个事情，它对系统传热量，但这个热量显然不是一个物理的热量，是一个信息意向的热量。那么什么意义呢？这个就不是很清楚。是不是说在计算过程中也有一些，比如说像类似像一些耗散的一个东西，就是说随机性啊或者什么，就是说这个需要一个刻画。
好，那我们接下来进入到第三个话题，就是关于自由能原理和强化学习 AGI 之间的联系。针对这块话题，大家可以发表一下各自的看法。
对，那个我先说，刚才我已经说了，就是说像卡尔还有另外一参会也说了，就自由能原理跟强化学习跟 AGI 跟 AI 或者 deep learning，实际上背后的基本原理是按我的看法是一致的，原因也是基于我们最近的一个工作，刚才也提到，涂叶海他们认为他们发现的东西，这个自由能统计物理学原理不适用，我们发现这个是不对，他把有些东西设定错了，就是整个这个原理，这套结构可以用于强化学习啊 AI deep learning 可以用过去，背后是一样的，所以我呢有一个观点，就自由原理和后面对应的基本动力学规律，实际上也是 AI 也是 deep learning 背后对应的基本规律。
我感觉我也可以说一点，就是有关这个自由能原理和强化学习的一点东西。就是当时我给 Friston 做过一次他们那个 UCL 那边讨论班的一个汇报，然后当时我讲的就是自由能原理和强化学习之间的一个关系嘛。然后讲完了之后，他就给我提了一个观点，说他对就是我说这个自由能原理和强化学习怎么对比感到不太舒服。他觉得说强化学习可能更接近于就是那个实现了自由能原理的那个主动推理框架的一个特例，就是包括我们后来在将那个强化学习基于模型的强化学习的一些公式和自由能原理它基本的那两个公式，那个变分自由能和预期自由能做对比的时候，就会发现其实就是从决策的角度上。强化学习它的目标函数那个奖励的信号，最大化累积奖励的那个信号，其实就相当于是预期自由能那个公式进行调整后的一个结果。预期自由能公式，刚才那个 Friston 可能很快速的跳过去了，就是大家可以看到它有不同的写法嘛，它可以写成是那个预期效用函数里的那个 risk 减去一个每个决策的 ambiguity 那个模糊度，或者说是一个就是一个信息增益再加上一个偏好项的形式。然后那个偏好项在自由能原理里面，它通常会被定义成一个就是智能体自身内部信念的一个函数，就是说它对某个状态偏好，那么这个偏好项就会大。然后在很多那个深度主动推理的研究中，其实把这个偏好项都用强化学习环境的那个奖励信号代替掉了。所以其实强化学习和自由能原理之间的关系，可能更接近于说，强化学习是将自由能原理这么一个框架进行了一个略微的简化后的一个结果。就是顺着这一点，就可以继续往下说，就是对强化学习的启发，可能 最基础的一点，可能我有点班门弄斧了，就是最基础一点就在于，我们可以去调整一下强化学习的它的一个目标函数，我们不只需要环境返回的一个奖励信号，也需要就是这个算法可以自发的通过这么一些内在奖励或者信息增益去对环境的状态进行一个探索，去降低这个对环境状态的一些不确定性。
对于这块儿，就是比如包括刚才郑权提到说，预期自由能里面两项，一项是这种信息增益，一项是和奖励就是和智能体的偏好或者它内在属性相关的这个一项。那其实这个内在增益在强化学习探索领域也是有，就近几年其实也是有比较多的工作，就是使用这种信息增益作为强化学习智能体，或者是作为这种 model base 的强化学习智能体的一个内在奖励。来去指导智能体的探索。那其实从这个角度出发，我感觉就是自由能原理，不管是从变分自由能，还是后面的这种期望自由能或者预期自由能，它们之间都是能和强化学习可能有个对应。那刚才说到，可以说，比如强化学习是自由能原理主动推断框架下的一种具体实现。那其实我有个问题就是说，自由能原理，如果说强化学习是它一种自由能，一种实现的话，自由能原理它能够在比如什么更多的地方去启发强化学习吗？就是因为不管是变分自由能还是预期自由能，它们的那些项都是能够对应上的。那自由能原理它有没有什么或者更多的地方能够去做一个启发？然后我还有一个想要讨论点，就是刚才其实汤老师也提到说，那个状态空间可能比较大，然后它的实际应用存在一些挑战这个问题。我觉得这个问题确实也是自由能原理存在的一个问题。就像自由能原理，它其实它把它叫做是一种就是规范性的理论，就它不是一个具体的一套框架或者说一套模型，它是一套指导我们去设计实验就设计模型的一套原则。那基于这个原则，其实结合具体的领域，就比如像我们如果想要研究神经过程的话，那它其实是有一个叫具体的神经过程理论。就神经过程理论的话，它在里面就是你需要定义它的一个状态空间，就根据我们不同的问题，我们需要去定义这个状态空间，然后基于这个状态空间，我们能够去写出它的生成模型。然后这个生成模型才是作为我们对这个对象它的一套描述。那其实它的问题就是有在于说它的状态空间可能会非常大，在针对一些实际系统的话，因为它是关于这种微观的状态，它是非常大的，所以在它的很多描述里面都是一些状态很小的一些 toy model 来去作为举例。这可能也是它的一个局限。这是我的一个理解，所以从这角度来说，我觉得自由能原理和强化学习可能能够互相启发，就包括强化学习所使用的这种梯度，就是反向传播，可能能够去帮助用于改进，比如像自由能原理里面它去具体实现的这种消息传递算法，可能是能够有一些互相的启发吧。对，这是我的一些看法。大家如果没有更多意见的话，那我们可以进入到最后一个话题，就是自由能原理它面临哪些挑战以及它待解决的问题。好，那我们进入到最后一个话题，就是关于自由能原理面临的挑战以及待解决的问题。
然后我先说几句话吧，就接着刚才张军老师的，他自由能原理也接着那个雷汉老师的，他实际上需要一个明确的动力学框架，明确的动力学框架。那么我想很多老师也知道这个明确动力学框架，我在过去20年一直在推动的，我把它叫做演化力学，或者叫达尔文演化动力学，需要一个动力学框架。缺少动力学框架，自由能原理本身是不容易讲清楚的。这是我的一点意见吧。需要一个动力学普世的动力学框架。那么我个人推荐，因为这也是我20来年在做的演化力学或者达尔文动力学，这也是当初这个卡尔找到我要跟我合作的主要理由。
郝老师能推荐一下这方面的论文吗？
有，那个我不知道是不是在群里边的，那个不知道那个梁金老师是不是在？ 我可以把一些论文发在那个自然原理那个讨论群里面的。
敖老师之前在我们的读书会也讲过，然后那次也分享了很多文献，大家可以那次也是公开的，是第4期，大家可以去看一下回放。
对，因为刚才我把我的那个摄像关掉了，这个因为信号开起来以后，我这边信号很差，所以就强调就是说，第一个地方它需要一个动力学原理。
以及就是关于自由能原理它的一些被质疑的地方，然后在读书会的第3期，也有老师针对这方面来去介绍一些相关的论文的工作，针对自由能原理存在的一些问题，然后提出了质疑，以及卡尔·弗里斯顿的回应也都是有进行讨论。大家感兴趣的话，也可以去关注一下，就是这个读书会。其中一个就是我能想到的一个，就是当时提到了一个，就是这个马尔可夫坦这个概念，因为当时这个马尔可夫坦它是一个统计意义上的马尔可夫坦，但是实际上我们比如像生命，它是一个就是实体的一个这种物质的概念，这种实体的概念和统计上的这种独立性，它们之间是否是一致的，或者说是一样的，这也是存在一定争议，有一些论文针对这种点这些点进行一个讨论。
这是一个非常好的点，这也回到这个刚才我说的，如果你接受演化力学或接受达尔文动力学的话，这两点之间没有矛盾。
就我提一点，就是说，我觉得 Friston 的马尔可夫坦这个概念是，当然也不一定是他最早提出，我还没有追踪过，但这个概念他这个提出，他这个我觉得也是非常深刻的，就是说，他就是说认为你一个系统，你假如说要有一个内部控制的话，你要跟外界要隔绝的话，你一定要产生一个它对于外界的要有一个表征，而且这个表征要 conditional independent。所以呢，这个就是说，统计或者在概率意义下，这个条件独立的话，这个事情当然你可以数学上来定义这件事情，对吧？那么他的意思就是说，你现在要做一个系统设计这个角度来讲的话，这个条件独立的话是一个非常关键的一件事情。
我想稍微再加一点，就是，实际上他讲的这种有些智能系统的它 predictive coding 啊，就是它能够超前预测，这个有可能是，就是说到底是一个涌现行为，还是说一个 design principle，这个也是非常有趣的课题。就是说实际上我总的来说，大家不要看好像这个自由能原理好像就已经板上钉钉了一样。这个是一个我觉得挺有意思的想法，但是这条路到底能走多远，实际上是看这个 community。我觉得这个特别高兴，这么多年轻人参与哈，然后 fascinated by 这个 principle，which is not actually formulated in detail。所以我觉得这里面真的是有很多空间可以继续做研究，而且是现在想法也都很有趣，但有趣的想法需要实践才能把它不断完善，就是我觉得这个大方向还是挺有意思的，但是我觉得希望能有更多真正的落地的成果。
对，因为我是更多从强化学习角度看自由能原理的嘛，所以我感觉就是自由能原理现在一个从强化学习角度上来说存在一个比较大的问题，就是它其实没有把这个事情做得很 work，就是像传统的那个自由能研究，它做主动推理框架的更多的是就是用人去定义好它内部的一个生成模型，然后去实现一个自由能的最小化。然后他说这个过程可以去解释整体的一些行为，再包括说它加上了后面的一些深度学习的技术，它也是从就是验证理论的角度去说的，而不是说它通过自由能原理的指导能够把一个算法做得比现在的算法性能更强。对，我觉得就是要把自由能原理做得更加的 work 一点，或者说从强化学习环境的角度性能更好一点，也是一个很大的挑战。
对，我也觉得这个自由能原理感觉它更是一个大统一框架，然后它能够把好多东西统一，但是并不知道它有什么新的这个知识给我们。对啊，就是哪个问题是就是用别的方案解决不了，然后自由能原理它能给出更好的一个启发的。我觉得这个我不知道，我看了了解的好像目前还没有 是不是特别有这个扎实的这样一个例子？
是的，我也是这样的感觉，就是感觉自由能原理它更多是一种就是解释性，就比如我们在实际的这种神经系统里面，它去针对这个系统去设计状态之后，它去建模，然后能够解释一些现象，就它是一种这种模型能帮助我们去解释一些现象。但是如果说从机器学习、强化学习角度，从优化的角度来说，就运用这套原理，似乎确实像郑权说的，没有帮助我们。能够有一个就是超过目前强化学习算法性能的一个表现，这也是是可能存在的一些问题的。好，大家如果没有新的问题的话，那我们这次圆桌讨论就到这里结束，也非常感谢各位老师和同学的讨论，然后感谢大家的参与，我们这次的会议就到这里结束。